Hello and good afternoon to everyone. Welcome to this live session 1 for our online course Applied Thermodynamics for Engineers. And actually welcome from a very wet and windy Guwahati. Even as I am speaking, wind is howling just behind me, my wall. Now this course, the lectures which you are seeing, these are actually, it's not a new course, rather the lectures are recorded a few years back. However, as this course has attracted registrations every year, and most importantly, as the content and coverage of this course remains relevant to anyone studying any branch of mechanical engineering or allied subjects, or even to the practicing engineers, so this course continues. And while the same lectures are getting repeated over last 3-4 years, we are having fresh assignments, fresh question papers, as well as fresh interaction. And the objective of this live session, of course, is to, as the name suggests, is to have a direct interaction with all the participants. So anyone interested to have any kind of discussion, I shall be available with you for some time now. You can send your questions through the chat on the YouTube page, or if you want me to answer to any specific questions, or if you want me to explain any particular topic in some more detail, please write there. I shall be happy to answer to your queries. Of course, queries keep on coming through the course portal, which we have tried to answer, and to the best of my knowledge, whatever queries we have received till today morning, everything has been answered. Of course, the link that was shared as a part of this live session or during the preparation of this live session, there is one query which I am going to talk about very soon. And apart from that, anyone available here, if wants to ask anything, please carry on. Now, in this course, Applied Thermodynamics for Engineers, I guess we have completed 4 weeks now. I am slightly confused exactly which week is it going on, but probably it's the week number 5 that has just started. So I'll continue by considering that we have completed 4 weeks. That means we have completed 1/3 of the course. And I shall be having, by the time, it seems I have to wait a bit to get your queries. So by that time, I can have a summary of what we are doing in this course, what we have done so far, what we have covered, and trying to give a glimpse. And during that process itself, I shall also be responding to the query that I have received on the online page so far. So yeah, I have got a query on the online page. Please, or rather on the YouTube chat, I shall be responding to that. That's a very general one because someone is asking how to prepare for the exam. There is no magic formula for that. This being a very much an applied course, you have to practice a lot. All the questions that have been asked as a part of the assignment, please try to solve those questions properly, and also try to solve questions from any of the suggested textbooks. And if you are confident about the procedure of handling those problems, I guess you will also be able to perform very well in the exams. Now, in this course, as this is an applied thermodynamics course, so it has a prerequisite of basic thermodynamics. So in the very first week of this course, we had a review of the concepts of basic thermodynamics over 4 lectures. And there we have reviewed the most important concepts which are required to perform thermodynamic analysis for any kind of systems. Now, thermodynamics is the mother subject for any thermofluidic science related topic. And the principles of thermodynamics provide the basis for any kind of analysis that we would like to perform for what I can say, for analyzing any kind of system involving heat transfer or work transfer or any kind of energy related systems. So we have reviewed fundamental concepts like systems, properties, intensive and extensive properties, proper and the stored property, which is a characteristic of any system, as well as energy, I should say stored energy. हेलो, मैं ऑडिबल हूँ क्या? Am I audible? I guess I got disconnected for a short while. Has the link been restored? Hello, my technical team. Has the link been restored? Yeah, is it going now live? Okay, fine. Sorry to everyone. We got disconnected for a short while because of some power failure. Now, as I was talking about that in the first week of this course, we discussed about the fundamental concepts of thermodynamics, where we reviewed topics like heat and the concept of energy, concept of properties, and energy came as a follow-up of that discussion, where we talked about two different kinds of energies: stored energy, which is a property of the system, as well as the energy in transition, which refers to two different kinds of parameters: heat and work. Now, heat is the energy in transition which crosses the boundary of the system because of temperature difference. Because whenever you are talking about an energy in transition, there has to be some kind of potential by virtue of which the energy will cross the boundary from a system towards surrounding, or the other way around. Now, when that potential is temperature difference, then we call that heat. Whereas when the potential is something else, we call that work. And then we talked about the basic principles of thermodynamics. Like we talked about the first law of thermodynamics, which gives us a way of identifying energy balance. Means it is often very loosely said that the what I can say, often it is very loosely said that the first law of thermodynamics is nothing but a principle in energy conservation, but that is not true in every sense. But probably you can work out most of the problem by treating it as a case of energy conservation or a principle of energy conservation. Then we talked about second law of thermodynamics. In second law of thermodynamics, we got an idea about the direction of energy transfer, particularly the direction of heat transfer. And here also we got the idea which talks about the quality of energy in transition, that because first law can't differentiate between heat and work, which second law provides us that kind of differentiation. So these all concepts directly came from basic thermodynamics. So this first chapter was nothing but a review of basic thermodynamics. From the second chapter onwards, we started getting topics which are more relevant to the analysis of different kind of thermodynamic systems. Now, whenever we are trying to analyze any thermodynamic system, we must perform the calculation of the properties. And whenever we are trying to calculate the properties, we need to know the property relations. We need to have some kind of idea what kind of property relations that are applicable for any given system. And so their second and third week were focused on that. In the second week, talked about thermodynamic property relations, particularly Maxwell relations. And in that context, I will go back to the question that has been already asked in that online form. There someone has asked, why do we need to study the Maxwell equation? Now, if you note carefully, uh, the basic principles of thermodynamics are based upon certain properties which are somewhat abstract in nature. Like whenever you are talking about a first law based analysis, we use for closed system we use internal energy, whereas for open system we use enthalpy, both of which are somewhat abstract concepts and we can't measure them directly for a given system using any practical tools. Similarly, when you are talking about second law of thermodynamics, we talk about entropy. Now again, entropy is an abstract concept and we truly can't directly measure it. And that's where the role of Maxwell property relations comes into picture. Maxwell property relation provides us a way of estimating these properties, particularly entropy directly and enthalpy and internal energy indirectly, in terms of three properties which we can measure directly in practice: pressure, temperature, and specific volume. I repeat, these three properties, pressure, temperature, and specific volume, can be measured directly by, there are numerous practical tools for doing that. And once we have got a measurement of that, we can use that to get a measure of entropy directly using the Maxwell relation. And then we can use those relation to get some idea about the change in internal energy or enthalpy for any given thermodynamic process. And that's where the role of Maxwell property relations comes into picture. Similarly, in the third module, we talked about primarily the phase change processes, where we got the concept of saturation temperature, the subcooled state, the superheated state, the use of different kind of property tables that were introduced in the third module. There we also talked about the concept of critical point, compressibility chart, which the use of ideal gas equation of state as well as the non-ideal gas equation of state. Accordingly, the second and third module provides us a way of identifying all the relevant properties for any thermodynamic system and accordingly prepare us for analyzing thermodynamic systems. So in the fourth week onward, we started analyzing different kind of thermodynamic system, and there the first one that we had in our agenda was the air standard cycles, which we have already covered. There we talked about the Otto, diesel, and dual cycles, which are the ideal cycles for different kind of reciprocating engines. We have seen what are the ideal cycles, how to use that for analyzing practical engines. Like SI engine is having Otto cycle as its fundamental one, whereas the diesel engines of course have the diesel cycle as their basic tool and can also be the dual combustion cycles or dual pressure cycles. And using these cycles we get an idea about the idealized performance of these engines. Now in the module number 5, several real life factors will go in, so that we shall be talking about the fuel air cycles and actual cycles, which will add some correction factors on the performance of an ideal cycle and get more realistic estimate about the power produced by practical automobile engines. Now I have got some more queries in that YouTube link. We are having some issues with network and particularly about power failure, so please excuse us for that. There's a query that I can see where someone is asking, please tell the pattern of the exam. Now, you have seen in the assignments, we are having questions in the form of MCQs and some fill in the blank kind of questions where we are solving some numerical problems. Now, exam paper also will be of the same form, the final exam, where if I remember correctly, it will be 100-mark paper comprising of 50 questions, where many questions will be of the MCQ form. That is, you have to choose correct answer among multiple given options, and also there will be quite a few questions, particularly the numerical questions, where you have to solve the problem and write the numerical answer in provided blank space. So the exam paper will be very similar to what you are getting in the assignments. Is there any new question coming? I have to wait for that. Because of this repeated failures, I'm also unsure how it's going, because questions are not coming to my end. Maybe I can keep on talking about the fourth module that we have just completed. In that fourth module, you have encountered the air standard cycles, where we have talked about basically the ideal cycles for automobile engines. But as automobile engines definitely don't run with air as the working medium. Rather, they use combustion gases as their working medium. Combustion gases produced by burning some kind of liquid fuels, like it can be petrol or diesel. Petrol in SI engine, spark ignition engine, diesel in CI engine or compression ignition engine. However, in these air standard cycles, we consider air as the working medium for these cycles, which is also assumed to behave like an ideal gas with constant specific heat. And then we try to perform their analysis following standard principles of thermodynamics, particularly energy balance. And also we analyze each of the process separately, combine them to form a cycle. Like in case of Otto cycle, we have seen that an Otto cycle comprises of 4 processes, and this what are the nature of the 4 processes? I guess you definitely remember the 4 processes that we encounter in an Otto cycle. There are 2 constant volume processes and 2 isentropic processes. Means both heat addition and heat rejection are constant volume in nature, whereas the expansion and compression both are isentropic in nature. And once we individually analyze each of these processes and then combine their performance, I should say combine their output, then we get the combined view of the net cycle. Like during the constant volume processes, we know as we are dealing with a closed system, if the volume is constant, there will be no work associated with those processes. So the work that we have to deal with whenever we are talking about an Otto cycle, those comes only during this isentropic during, and we get the work output during the expansion process, and their difference is the net work output that we can get from an SI engine. That's what we analyze. Similarly, when we are analyzing an compression ignition engine, here the heat rejection still is in constant volume mode, however heat addition is in constant pressure. So during the constant pressure process, we of course have work interaction involved as well, and therefore here the net work output will take care of the interaction between these 3 processes. But we also, as 2 processes, the heat interaction still remains associated with only those heat addition and heat rejection processes. And as we know from the first law of thermodynamics, that the cyclic integral of work interaction has to be equal to the cyclic integral of heat interaction. And therefore, instead of performing work interaction for each of these 3 processes separately, we can still continue to calculate the heat interaction during that heat addition and heat reaction processes, and their difference is going to give you the net work output as well. The net amount of heat going into the system will be equal to the net amount of work output that we are getting from the system. And the last one was the dual combustion cycle, where the heat addition, which actually very closely resembles a real life CI engine, where a part of the heat addition process is in constant volume and a part of the heat reaction process is in constant pressure. So if you think carefully exactly how combustion may be happening in case of a CI engine, where we are injecting the liquid fuel. As the liquid fuel is injected, a part of that burns immediately. Means a part of that gets participates in combustion almost instantaneously before the piston can change its position. So that part we assume or we model as a constant volume heat rejection, and remaining part of the fuel participates in combustion as the piston moves downward. So the next part of heat rejection, or I should say the next part of heat addition, is a constant pressure heat addition. However, the finally heat rejection process continues to be in constant volume mode. So here we have three processes during which you are having heat interaction. The heat addition broken into two, a constant volume part and a constant pressure part. And finally, that heat rejection process in constant volume mode. And there summary gives us the net work output. In the YouTube link, at least whatever feed I am receiving, I am not having any new query coming in my way. I shall still be waiting for some time. I'm not sure whether it is an issue with the internet that I am having here, or whether queries are really not coming. But of course, this is not the last live session, rather only the first one, and we are supposed to have 3 live sessions. So we shall be having future interactions as well during our live sessions. Besides, anytime if you have any query, you can always write in the course portal. And also, you can always write directly to me. I shall be happy to respond to any queries in this regard. If queries are not coming, in that case, probably I would like to close this technical session. I shall be waiting for a minute maybe, or just for a few seconds more before I would request our technical team to close down this session. Yeah. Yeah, please. Whenever we are having any kind of online interaction, there we always face these issues with the network, and it can be quite inconvenient. But still, I shall be trying to have as much interaction as possible. Anyhow, whenever we are means in online mode, it is never possible to have interactions equivalent to, or even nowhere close to what we get in a real life situation. Now I have got a query here from Sudhakar Gopala, who is asking about a doubt regarding linear cycle versus Otto cycle. Okay, linear cycle is a very less used one in thermodynamics, since it is primarily used for modeling the pulse jet engines. And it is characterized by 3 cycles, whereas in Otto cycle or diesel cycle, they are characterized by 4 distinct cycles. Sorry, not cycles, 4 distinct processes, I should say. That 4 distinct processes that suits the operation much easily to any real automobile engines, because we are directly talking about, like if you are talking about a 4-stroke cycle, 4-stroke engine, then we can easily relate these cycles with these 4 steps of should say we can easily relate the strokes with the 4 processes involved in the cycle. However, in linear cycle, we generally have only 3 processes. There is heat addition via constant volume, and then we have an isentropic expansion process and constant pressure heat rejection process. It doesn't have any kind of compression process as such, because again, it depends on the application that we are talking about. Here, like in case of Otto cycle, in ideal Otto cycle, there is no rejection as such. The same air is getting utilized. In practical cases also, the fuel air mixture that goes inside an SI engine, that first need to be compressed to a high pressure level, because the high pressure also helps to increase the temperature, and once we go to high pressure level, that facilitates the expansion back to the surrounding pressure on lower pressure level. But in case of a linear cycle, that doesn't include a compression process. It has only a heat rejection, or I should say a heat addition, which is at constant volume. Of course, there will be later on there will be the heat rejection, that is at constant pressure, and there is the expansion process. It is very much a simplified model. Its thermal efficiency is much lower traditionally compared to the Otto or diesel cycles, and therefore it is not that common in case of practical use. At least in common thermodynamics, we hardly deal with this particular cycle. Now, if you are interested to know more about these cycles, please write back to me. I shall be happy to come up with more details and also about the procedure of analyzing this particular one. But again, I don't think there is any confusion with Otto cycle, because the nature of the cycles are completely different. Any further query? The last query that came from Sudhakar was quite some time back. So I guess we can close down the session if our technical team agrees. I'd like to request them to close this session. Okay, thank you very much. Hello. Huh. Okay, sure.